Okay, now, this is a simple circuit with only one piece of load, which is one single resistor. But in most cases, we would have several or even a large number of resistors in the same circuit. Okay, how does one combine them? Let's see here. Let's see here. Just like the case of capacitors, okay, we can combine resistors in different ways, in series and in parallel. Remember how we studied them in series and parallel? Okay, in the case of capacitors, you recall that if we connect two capacitors in parallel, what happens to the equivalent capacitance? Well, it's just like adding more areas, right? Adding more areas to store charge, so the capacitance will increase, which is C1 plus C2. But in the case of connecting two capacitors in series, we actually get a smaller capacitor because effectively, for each capacitor, now you have to share the voltage. So for each one, you get a smaller amount of voltage. You add the voltages up. You don't add the charges up. Okay, so each one of them will have a small amount of charge stored because they have a smaller amount of voltage across them. They have to share that voltage. Okay, so again, connecting two capacitors in parallel give you a bigger capacitor. Connecting two capacitors in series give you a smaller one. Is that the case also for resistors? Well, common sense tells us not really. Okay, for two resistors connected in series, a current will have to flow through both of them. Right? Have to flow through both of them, has to travel longer, and therefore you can imagine a greater equivalent resistance. Well, if they're connected in parallel, then you can imagine a current can split two ways, and therefore it's just like decongested traffic, right? By opening one more lane. So therefore you can imagine the resistance to be smaller. Okay, so that's the qualitative understanding. But exactly how does that work? All right. Now, suppose I have two resistors connected in series. That's one after another. Okay, from point A to point B, you go through R1 and you go through R2. No branching out. Okay, no branching out. It is equivalent to a single resistor called R equivalent between points A and B. Now that means that if I hook this to a battery and I hook that one to the exact same battery, I would draw the same what? The same exact current. Okay, so this current, and that current, they're all the same. Okay, and current here and here flowing through both resistors would be the same because it's a single branch. No current flows sidewise. Okay, now, what is the equivalent resistance? Well, all I have to do is calculate I. Okay, calculate I. Let's see what I is equal to. It's proportional to the voltage difference between here and there. The voltage difference between here and there, we call it V. And that, of course, is the sum of the voltage difference across the first resistor plus that across the second one. Okay, just like you go from the third floor down to the second floor and then get down to the first floor, the drop in height in elevation would be from the second to the third to the second plus that from second to the first, right? So it's V1 plus V2. Okay, V1 plus V2. And V1 is the voltage difference across the first resistor. And there's a current I flowing through it, and of course from Ohm's law, applied to this resistor alone, we know what is I equal to, or what is V1 equal to. V1 equals I times R1, right? Ohm's law applied to this resistor, so it's I times R1. Similarly, what is V2? Voltage difference across the second resistor. Okay, Ohm's law applied to that tells us it's I times R2. Again, it's very important to realize that this I and that I are the same. I didn't call it I1 and I2. They're just the same. Okay, so take that I out. It is I times what? R1 plus R2. That's how we find V. Okay, meanwhile, you hook up the same battery which provides the same resistance V, same potential difference V across the equivalent resistor. So it's the same V, and you have a single resistor, so it's just I times R equivalent if you apply Ohm's law to it. Okay, so what is R equivalent then? R equivalent from here, by definition, V over I. Right? But wait a second, I know what V over I is. This is V, this is I. Move that I over. Don't I get V over I? What is that equal to? R1 plus R2. Okay? So, as our intuition tells us, the equivalent resistance is greater, it's just R1 plus R2. Okay? that is when you have two resistors in series. If you have 3 and 4 more, what do? Well, you have to keep on adding I1, R1 plus R2 plus R3 and so on. So, in general, for series, R equivalent equals R1 plus R2 plus R3 plus. This is the most general formula. Okay, for a bunch of resistors connected in series. And this agrees with the previous analysis that you saw here. In this case, you can think of the circuit now as two resistors connected in series, small and big R. Why do we know they're connected in series? Because you got one unbroken branch, okay, a single branch connecting both resistors. No branching out, a single Y connecting together, one after another. So these are in series, and therefore the equivalent resistance is just big R plus small R. See here? So that makes sense. And another way to understand this is, you know, for a material of resistivity rho, we can machine it into a resistor. Or if I know the resistivity and I know the length is L and the area is A, right? Now, suppose you have several one of these resistors in series. The same material, same cross section. Okay? If you connect in series, it's the same as making the resistor longer, right? So instead of L, now I have L1, L2 plus L3 and so on. And this is how you sum it up, right? If you replace L with L1 plus L2. Okay. So that makes sense. But it is kind of similar to the case of two capacitors in parallel, not in series. Okay? So please do not confuse that. All right. Now, let's connect the resistors in parallel and see what happens. Well, what is your intuition as far as the equivalent resistance? Well, now you have a current which branches out two ways. Here's I1 and here's I2. Okay? What can you say about I1 and I2 versus I? Well, look at this junction. Okay, look at this junction here. There's a current I flowing in. It has to branch out and become I1 and I2. I is related to I1 and I2. The reason why current flows out is because there's this current flowing in. So, I must equal to I1 plus I2. If that were not the case, if I were greater than I1 plus I2, that would mean more current flows in, less current flows out, and then what do you think is going to happen to that dot, to that junction? Well, over time there will be an accumulation of charge, right? Because more charge is flowing, less charge flow out. And that is not the case. Okay, here's just a point. It cannot contain any charge, so therefore whatever flows in must flow out at the same time. Okay, so I equals I1 plus I2. And as far as I1 and I2 are concerned, I can apply Ohm's law to each of these two resistors. You see, both of these resistors are exposed to the same potential difference across points A and B, which I call V. So V is equal to I1 times R1 if you apply to the first branch, and I2 times R2 if I apply to the second branch. Okay, in other words, let me write it down. V equals I1 R1. It is also equal to I2 R2, right? I can then solve for I1, which is V over R1, and I2, which is V over R2, and plug in back here. So what is that I1 equal to now? V over R1, V over R1 plus V over R2. Okay? Which I can write as V times 1 over R1 plus 1 over R2. Okay? But wait a second. What is the equivalent resistance? If I replace both branches with a single equivalent resistance, the resistor, just like this, then isn't it true that I would have to be V divided by R equivalent? Right? Now, and then if you compare these two, the first one says I equals V times this guy. Second type, I equals V divided by R equivalent. If you relate these two currents expressions, you will get 1 over R equivalent equals 1 over R1 plus 1 over R2. Okay? And that is when you have two resistors connected in parallel. If you have 3 or 4 more connected in parallel, you're going to have to just keep on adding. 1 over R3, 1 over R4, and so on. And this formula reminds us of how we calculated the equivalent capacitors connected in series, okay, not in parallel. So connecting capacitors in series is somewhat like connecting resistors in parallel, okay? R equivalent is less than R1, it is less than R2, it is in fact less than the smallest of all these R's connected in parallel. Make sense? Because you see, the reciprocal of R equivalent is the sum of these reciprocals. Therefore, it is greater than any single one of these reciprocals, and therefore R equivalent itself must be less than any of these resistors. Okay? And that also makes sense qualitatively, once again, because as you add more branches, the current does not have to be congested anymore. They are, it's spread out among many branches. Each branch is less congested, and therefore that will decrease the resistance. You can understand this from this formula. Okay? Which quantity do we sum up now? Well, suppose you have a whole bunch of resistors made of the same material, of the same length, but they have different area. Okay, they have different area. If you connect these resistors in parallel, what is the total area over which the current can flow? It will be A1 plus A2 plus A3 and so on. So basically adding the areas up. That's what you do. Okay, of course, you cannot add areas in the numerator, in the denominators. What you do, you can flip them over. Okay, you can flip them over. So A goes like 1 over R, right? You flip them over. If you add A1, A2, A3, then you have to add 1 over R1, 1 over R2, 1 over R3, and so on. This is why you're adding the reciprocals up. Okay, so this is because you're adding the cross-sectional areas up. That's what's going on. Okay, now let's look at a real circuit which contains a combination of series and parallel. I have here 8 resistors, R1, R2, R3, all the way through R8, and I have 3 points of interest, A, B, and C. Now, let's calculate the equivalent resistance between, say, points A and C, points A and B, points A and D. Okay? Now, of course, the way we do that would be, if I want to measure the resistance between points A and C, I would connect a battery, positive terminal to point A, negative terminal to point C, and then see how much is the total current flowing through the battery, right? And then EMF of the battery divided by the total current would be the equivalent resistance. Now, let's look at points A and C first. If you connect a battery, positive terminal to point A, negative terminal to point C, you ask yourself, how many branches will be the current flowing from point A to point C? Well, starting from point A, there are 3 branches. You can flow this way, you can flow this way, you can flow this way. Okay, look at the first branch. The first branch goes through R1 and R2. The R1 and R2 are obviously in series. And the second branch goes through R3 first. And R3 is obviously in parallel with R1 plus R2. Right? And then these 2 branches will combine to flow through the same a single resistor R5. So this combo would be in parallel with R5 because the current has to flow through this combo first and then flow through R5. Now there's a third branch which bypasses all of this. It goes through R4, R8, R7, and R6 unbroken. So all these 4 will be in series. Make sense? Before they reach R. Okay, so how do I simplify them? Well, you can draw a simplified diagram if you want to, or you can just make sure you account for everything in your head carefully. First of all, R1 plus R2. Okay, that's R1 plus R2. Let's, for simplicity, assume all these are the same. They're all equal to R. So this will be what? You combine what? You get 2R, right? 2R, which then in combination with that one. Okay, so what is the equivalent resistance of this whole bunch? That will be 2R in parallel with R, so it would be 1 over R plus 1 over 2R, and you take the reciprocal of that, right? Now, if you did a little calculation, you find this 2 over 3R. So 2 over 3R takes care of this point and that point. You add that to what? To this guy, which is another R. So you get a total of 1 plus 2 over 3. That is 5 over 3R. That is from here to there. Okay? You have to then find the other branch, the branch that's left out, R plus R plus R plus R. They're all in series, so it's 4R. So you have one big branch giving you 5 over 3R, another big branch giving you 4R. Both branches lead directly from point A to point C. So these two branches, are they connected in series or parallel? Here's the first branch, here's the second branch. What do you think? Well, they're obviously in parallel. They both flow from point A to point C. So you're going to be connecting them in parallel. So what is the equivalent resistance for RAC? 1 over RAC would be equal to 1 over this guy plus 1 over that guy, right? So it's 1 over 5 over 3R plus 1 over 4R. Okay, you can easily finish this algebra and see what you get in terms of R. So that is how we calculate R between A and C. What about R between A and D? Okay, well, the idea is quite similar, but the answer will be different because this time, again, you start out with these three branches, right? Now, just like the first case, these two will be in series, will be in parallel with R3, okay? And then after that, they will get in parallel, in series with the next common resistor, which is R5. But the current does not flow to point C and stop. Rather, it continues to flow through R6 before it reaches point D, right? So you have this one big branch here, 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 leading to point D. And you have another branch, R4, R8, R7, and you reach point D. Okay, so again, we have two big branches. The first branch, first we have to go from here to there, and we already know what that is. That is 5 over 3R. I'm sorry, 2 over 3R. Okay, I'm sorry, 2 over 3R from here to there, right? Once you get 2 over 3R, you have to add to this R. That will give you 5 over 3R. But that's not the end. You have to add another one before you can reach point D. So it will be R plus 5 over 3R. So the entire branch covering this guy, this guy, this guy, this guy is R plus 5 3R. So it's 8 over 3R. Right? Covering R1, R2, R3, R4. I'm sorry, R1, R2, R3, R5, and R6. That is one branch. Another branch, R4, R8, R7, and that's it. You reach point D. You add these three up in series. Okay, they're unbroken, right? It's the same chain. So it is 3R, and that is connected in parallel with the that branch. So what is the equivalent resistance? Would be this guy and that guy in parallel. So that tells us 1 over RAD is 1 over this guy plus 1 over that guy. So it's 1 over 8 divided by 3R plus 1 over 3R. Okay? So the answer will be different, but the idea is the same. Alright, we can also calculate the equivalent resistance between A and B. Now, in this case, you ask yourself, how does the current flow from A to B? Again, there are always three ways for the current to flow out of point A. One of them leads directly to B. Okay, that's through R3. Another one flows through R1 and R2 and also reach point B. Okay, and these two branches are obviously in parallel. And there's a third branch going from here. R4, R8, R7, R6, and R5 has to flow all the way through points D and C before it reaches point B. And all these three branches are in parallel. Do we agree with that? They're all in parallel, right? Here's the first branch going from A to, actually, first branch going from point A to B, point B, second branch going from A to point B, and the third branch coming all the way out, coming back to point B. So these three branches are in parallel. So therefore, 1 over RAB, okay, the reciprocal of all these three parallel branches. The first one is just 1 over R. Just 1 over R. It's this guy. Next one is 1 over 2R, right? Is that one. And what about the third one? 1, 2, 3, 4, 5. All 5 in what? In series. It's 1 over 5R, okay? And you can solve for RAB from there. So, this is an example where the combination can be broken down, can be simplified into a bunch of series and parallel. So be careful about how you can count branches. Okay, like here, this branch, this branch, this branch. Keep a clear mind. If something branches out, then we cannot say it's in parallel, in series anymore. For example, R1 and R2, they are in series because there is nothing broken between them. But when you go to here, it's a different story because it branches out. before reaching R5. So therefore, we cannot say that R1 and R2 are in series with R5 anymore. Okay, because it does branch out before reaching R5.